Hi, everybody. And today I would like to discuss solutions of some problems from the second assignment. And first, let's consider problem 1.284. This problem is interesting because it's a combination, it presents a combination of a gyroscope and a non-inertial reference frame. So you have to use both formulas for gyroscope precession, and you have to take into account that this precession takes place in a non-inertial reference frame. So the problem statement is as follows. A gyroscope, a uniform disk of radius r, at the end of a rod of length L, so r is given as 5 centimeters, and the length of this rod is given in the problem as 10 centimeters. A gyroscope is mounted on the floor of an elevator car going up at constant acceleration, and the acceleration is also known as 2 meters per second squared. The other end of the rod is hinged at the point O. So here is a hinge. It means that the rod L can freely rotate about point O. The gyroscope precesses with an angular velocity making some n revolutions per second, 0.5 revolutions per second. Or it's possible to use RPS abbreviation, or RPS revolutions per second. Neglecting the friction and the mass of the rod, find the angular velocity of the disk. So we have to find the angular velocity, omega, with which this disk is rotating. The mass of the disk is not given. We don't know the mass of this disk, but it's rotating with angular velocity omega, and we know the radius 5 centimeters, and we know that this disk is attached to a rod, or which is an axle of rotation, and this axle of length L, 10 centimeters, is hinged here so that it's somehow attached to the floor, and this is the floor of an elevator which goes up with acceleration. I don't know why do they use omega, why do they use this letter omega for acceleration. I don't like it. I use omega for angular velocity, and acceleration should be, let's denote it by A, which is much better for me. Well, actually it makes no difference, but I would like to denote acceleration by A and angular velocity by omega. So the situation is clear. We have a lift, elevator car going up with acceleration A, so it's accelerated upward, so that everything that takes place here in the elevator car is going on in a non-inertial reference frame. This is a non-inertial system. And what happens here? A disk rotating, fixed to the axle, which is hinged on such a vertical rod. And we know the angular velocity of precession of this gyroscope. I will free this place to show the precession of the gyroscope. What is a precession? It means that this point is precessing. It means that this point describes a circle. What is the gyroscope precession? You know very well. You have seen it. You have observed it. The gyroscope. If it was not rotating at some angular velocity, then such a construction would simply go down under the influence of gravity, forces of gravity. It just will fall down on the floor. But if the gyroscope is rotating at very high frequency, then there will be the phenomenon which is called precession. That is, the rod to which the gyroscope is fixed and which is hinged here at point O is rotating slowly at much slower angular velocity than omega. So the movement of this rod along the circular trajectory takes place at some angular velocity which I will denote by capital omega. It's a slow motion. This rod slowly turns about and makes some 0.5 revolutions per second. That is one total revolution in 2 seconds. That's a slow motion. And the disk is rotating at very high angular velocity omega. We have to find this omega. We have to find what is the angular velocity of rotation of this uniform disk. So, what law of physics should be applied in this problem? Certainly, the law of momenta, that is the rate of change of angular momentum of this disk, equals the torque of external forces. As the disk is uniform and symmetric with respect to the axis of rotation, then angular momentum can be presented as a moment of inertia times angular velocity. Such a presentation, such a formula can be applied only in case the disk or a body is symmetric with respect to the axis of rotation. If this rotating body is non-symmetric, then this would be incorrect. And what should be used instead of this? Instead of this formula, you should take into account that the moment of inertia will become a tensor of inertia. We discussed this issue in detail. For non-symmetrical bodies, that will be a tensor of inertia. And tensor is a matrix which should be multiplied by a vector. And the result of multiplication of matrix by a vector will be another vector which is not parallel, in general cases, not parallel to omega vector. That's the very important point in this problem, that moment of inertia in our particular case will not be a tensor of inertia. It will be just a number, just a coefficient here, because the rotating body is symmetrical with respect to the rotation axis of rotation. Well, what about vector omega? If it rotates in this direction, then vector omega will be directed here. And so the first equation, the first line will be written as, after differentiating vector L, we will obtain constant coefficient I, which is a moment of inertia of this disk, times omega dot, which is angular acceleration. And omega, that is certainly a vector, and that will be equal to the vector of external forces, which is by definition a torque of external forces. By definition is vector product of R times external force. What external forces act on this disk? to the center of mass of this disk, a force of gravity is applied. That is the external force F, and F is sure to be mg in magnitude. In direction, it's directed downward, vertically downward. And what is vector r here? Vector r is the vector from the point of rotation, point of suspension of this gyroscope towards the center of mass. That will be vector r. So if we take vector product r times f, using the rules for vector product, we will have to rotate vector r until it coincides with vector f, and this rotation will give you the motion of a screw, rotation of the screw, which will go in this direction perpendicular, which will be displaced perpendicular to the blackboard. So if you rotate the screw clockwise, in this particular case, vector r is rotated until it coincides with vector f. If you rotate in this direction, if the screw is rotated clockwise, then it goes there, perpendicular to the rod. And that will be the direction of change of omega, or change of this vector, angular momentum. So vector of omega looks here, but it will be changed in this direction, perpendicular to the rod. So that this point will go here. And then after it has changed, again, the change will be there. And so every short period of time, the change of vector omega will be such that vector omega will rotate, and the end of vector omega will describe a circle. Such a motion is dictated by this equation. The precession, this equation describes the precession of gyroscope. Now we have to work with this mathematical formula. We have to simplify it somehow and make it suitable for calculations. Nothing more. That is the main physics law, which is written here. We have to use this law, but in order to use it, we have to somehow transform it and simplify it. What will be the simplification? First of all, we can go to magnitudes of vectors. These two vectors are perpendicular, and when you take the vector product, you will have the magnitude of vector r times magnitude of vector f times sine of angle between them, and sine of 90 degrees will be just 1. So if we go to the magnitudes, we will have here just r times f, and r is equal to L. That's it. So we will have here L, and f is mg. That's it. The magnitude of this vector will be L mg, where L is the length of this rod, the distance between the point of suspension, the point where the rod is hinged, to the center of mass of the disk. And here, omega dot, what is it? Omega is the vector which is rotating about vertical axis, so that omega, vector of omega, is directed here vertically. This rod L is rotating in such a way that it goes around the vertical axis of rotation. This is the axis of precession of gyroscope. So the axis of rotation of disk L is horizontal, and the axis of precession is vertical. Because rotation is very quick, and this is one sort of motion, and precession is another sort of motion. Another kind of motion has its own axis of angular velocity. So if we have omega, vector of omega, rotating, and rotation is the only change in omega, it does not change in its length. The magnitude does not change. Only the direction of this vector changes as it turns along circular orbit, along circular trajectory. So in this particular case, that omega will be a vector product of the capital omega, the angular velocity of precession, the angular velocity of rotation of rod L, times vector L. And if you take this vector product, you will have, again, according to the rules of finding a vector product, you will have to take the vector capital omega and rotate it until it coincides with vector small omega, and that will be the direction of rotation of the screw, and the screw will go there perpendicular to the blackboard. So the direction of this vector will coincide with these small arrows which I indicated here. That's actually representing the true direction, the true change in this vector, which we have already discussed. The change in this vector occurring due to the external, the torque of external forces. So, and as we go to the magnitudes, then the magnitude of this vector will be just omega capital times small omega, because these two vectors are perpendicular to one another. So the magnitude of the length of this vector product will be just the length of the first vector times the length of the second vector. And sine of angle between them is unit, because angle is 90 degrees. Is that clear? I'm trying to explain every small step in the solution. So this vector equation, which looks complicated because it has vector products and vector quantities, can be simplified if we go to the magnitudes of these vectors. Then we will have moment of inertia I times capital omega times small omega equals LmG. That is the same equation written in scalar form when we go from the vector form to the magnitude, to the length of these vectors. Well, this is a very considerable simplification of the original equation, but that's not the last simplification we need. We don't know capital omega. It's not given in the problem. What is given in the problem is the number of revolutions per second, 0.5 revolutions per second. But angular velocity can easily be related to revolutions per second, because 1 revolution per second is 2 pi, is the angle of 2 pi. So that if you take 2 pi and multiply it by the number of revolutions, this is the angle related to a single revolution, and this is the number of revolutions per second. So that will be the total angle of revolution in radians. That will be exactly the capital omega. So instead of capital omega, we can use this expression 2 pi n. N is given in the problem, in the statement of the problem. And so we need to find small omega. We need to find small omega. The only thing remaining to be done here, so capital omega is just 2 pi n. The only thing remaining to be done here is to present the value for the moment of inertia of this rotating disk about the axis of rotation, which is perpendicular to the disk and going through the center of mass. You know very well this formula. This is mr squared divided by 2. That's the moment of inertia of such a disk about the axis which is perpendicular to the disk. There are other axes. You may calculate the moment of inertia with respect to this axis of rotation. That will be mr squared over 2. But if you calculate it about this axis of rotation, the moment of inertia will be different. you know it will be, it can be calculated using the Huygens-Steiner theorem. But there are other axes of rotation, for example, this axis of rotation, so that the disk rotates in such a way. The moment of inertia will be different. It depends on the axis of rotation. So in our particular case, that will be the moment of inertia. And so we can find the final answer for small omega, for lowercase omega. That will be LmG divided by 2 pi n and moment of inertia, which is mr squared divided by 2. Therefore, 2 will go to the nominator of this formula. M will cancel. And what remains here? 2Lg divided by 2 pi n r squared. Again, 2 cancels. And all the remaining quantities in this formula are given in the problem. They are known. You can take G as 10 in the International System. So let's do this calculation. L is 10 centimeters. I will use the International SI system. So I will have to express this L in meters. If it's 10 centimeters, it's 0.1 meters. G is 10 meters per second squared divided by pi, 3.14 times n. N is given as 0.5 without any units. And r squared, r is 5 centimeters. 5 centimeters is what? Is 0.5 meter, and that should be taken squared. I will continue from here. So 10 times 0.1 is just 1, approximately 1, exactly 1, and divided by 3.05. I will take pi as 3, so multiplied by 0.5, that will be just 1.5. And what is 5 squared? 5 squared is 25, and I have to divide by 100 squared, which is 10 to the 4th power, which goes to the nominator. And if you calculate this, you will find it to be about, well, something like approximately 300. So this is n revolutions per second. So actually 1 second will go here, certainly. And after you look at the dimensions, you will see that meter cancels, because here we have meter squared, and 1 second also cancels. And what we'll have second? Radians per second. So this is radians per second, about 300. Well, just maybe a little bit less radians per second. How many revolutions per second? One total revolution is about 2 pi radians, about 6. So 300 radians is about 50 revolutions per second. So this disk rotates at 50 revolutions per second. That's quite a large angular velocity. Any questions? Is everything clear? How to solve such problems? Whenever you have a problem on gyroscope, you will have to use this law of physics. All the problems on gyroscopic motion, on precession. Oh, I have forgotten about one important thing, and nobody told me about it. What about acceleration A of the elevator cabin, elevator car which goes up? With acceleration A, it means that the force of gravity, I've absolutely forgotten about it. I told you in the very beginning, and then it somehow slipped away from my consideration. So everything is going on inside the elevator cabin which goes up with a given acceleration of 2 meters per second squared, according to the statement of the problem. So actual acceleration, actual weight of this body inside the elevator cabin will not be mg, it will be mg plus a, because this is a non-inertial reference frame. So you will have to add here mg plus a everywhere. So this will be mg prime. It's not an acceleration of free fall on the surface of the planet. That will be an acceleration of free fall inside the elevated car. That will be larger by 2 meters. And so everywhere we will have this new acceleration because everything is in non-inertial reference frame, and that will be g prime everywhere. And it will be 12 instead of 10 meters, 12. And so it will be 1.2 here. Well, it doesn't drastically change the result. Approximately the same figure, approximately the same final figure, because the acceleration has not changed considerably, just by 20%. Just by 20%. Anyway, you have to take it into account if it's given in the statement of the problem. Another problem to be considered today will be 1.113. That's an interesting thing. So the next problem will be 113. A horizontal smooth rod, AB, rotates at constant angular velocity, omega of 2 radians per second, about a vertical axis passing through its end A. So this is the axis of rotation. Vertical axis. It means that the picture is in horizontal plane, that is on the surface of the table. This rod lies on the surface of the table, and it can rotate about point A, about this vertical axis, with a given angular velocity. There is a freely slipping sleeve. You may imagine the sleeve as a small ring which is on this rod, and this small ring can slide without friction along the rod. You may call it a sleeve or a small ring which is on this rod. It can slide without friction. So this small ring of mass, of given mass am, 0.5 kilograms. Oh, so it's not very small ring, it's 0.5 kilograms. It's a sleeve. Okay. originally the sleeve was given some velocity with respect to the rod, the original velocity of 1 meter per second. From point A, this ring was pushed with the initial velocity v0. And then it starts moving along it starts sliding along the rod, and the rod is rotating. Find the Coriolis force acting on the sleeve in the reference frame fixed to the rotating rod at the moment when the sleeve is located at the distance r, of 50 centimeters from point A, from the rotation axis. That's it. So the rod AB rotates not by itself. There is some mechanism which provides for rotation, which ensures that this rod rotates at constant angular velocity. It rotates regardless of whatever happens here, whatever happens with the ring which slides along the rod. It rotates at constant angular velocity, and the ring slides along the rod without friction. What happens to this ring? We can imagine originally it was moving from point A, and as the ring moves along the rod rotates. So the trajectory of the ring will be something like that. The rod rotates and the ring slides along the rod. So when the rod was at this angle, the ring was here. When the rod was at this position, the ring was here, etc. The ring slides along the rod farther and farther from point A with some acceleration, certainly. And if the ring is accelerated, then there is some force acting on the ring. The force acting on the ring is exerted by the rod, and therefore the ring, there is another force according to the third Newton's law, which acts from the ring on the rod. One force is applied to the ring, and another equal and oppositely directed force is applied to the rod from the accelerating ring. So two forces always present there according to the Newton's third law, because of the interaction between the ring and the rod. Okay, so the ring flies along such a trajectory, and this trajectory is observed by an observer who is fixed, who is not moving, in a laboratory attached to the earth, to the floor of this building, for example. We will see that the trajectory of the ring is that approximately. But what will be seen from the point of view of an observer who is rotating together with this rod? Observer who is rotating together with the rod will see the ring going out and out farther and farther along the rod and flying away. But this rotating reference frame will be non-inertial reference frame. Anyway, in a non-inertial reference frame, many things happen. We live in a non-inertial reference frame on the surface of the Earth. The Earth is rotating, so whatever happens in our planet is occurring in a non-inertial reference frame. We don't notice it every day because the angular velocity of Earth's rotation is small. It takes just 24 hours to make a complete revolution. One revolution in 24 hours. But anyway, this is, strictly speaking, a non-inertial reference frame. This is also a non-inertial reference frame, rotating much quicker at a much higher angular velocity of 2 radians per second. What is 1 radian? What is 1 radian? Well, it's about close to 60 degrees, just a little bit smaller than 60 degrees. So 1 radian is this angle. And 2 radians per second is about 120, just a little bit less than 120 degrees. So in 1 second, it makes actually 1/3 of a total revolution. So this rod makes a complete revolution in about 3 seconds, approximately. You have to imagine at what velocity, at what angular speed, what angular velocity is the rod rotating at angular velocity, about 1 revolution in 3 seconds, approximately. So, what law of physics governs the motion of this ring along the rod in rotating reference frame? In rotating reference frame, if you fix any object like this ring here in this point, you will see that there is some force acting on it, a force of inertia. You can feel this force if you sit in this point. You will feel that some force is trying to push you away. You will feel it, and in order not to slide, you will have to keep hold firmly in order to remain at the same point on rotating disk, on rotating rod. So there is a definite force which is sometimes very strong. And this is a centrifugal force. There is a force, centripetal force, from the point of view of an inertial observer who is in the laboratory reference frame. We will see that this fixed body goes along the circular trajectory, and there is, in every point, there is an acceleration directed to the center, and this is a centripetal acceleration from the point of view of a centripetal acceleration from the point of view of a laboratory observer who is not moving with respect to the Earth. In an inertial reference frame, there is a centripetal acceleration, but in a rotating reference frame, there will be a force which will be attributed to a centrifugal acceleration from the point of view of the rotating observer who is here in non-inertial reference frame. And this, if centripetal acceleration is omega squared and radius of this orbit, then the same will be a centrifugal acceleration, but it will have opposite direction. But in magnitude, it will be the same. So the force acting on this ring will be ma according to Newton's law, second law, and it will be m omega squared r, where r is the distance of the ring from the center of rotation, from the axis of rotation. So at whatever distance r the ring is found on the rod, there will be such a centrifugal force acting on it. And so there will be such an acceleration of this disk directed away from the axis of rotation. And the acceleration is what? Is the second derivative of distance r. If this is the distance, if this is the r denotes the distance of the ring from the axis of rotation. So the second derivative is the acceleration, and the acceleration is known. It's omega r. So we have this equation, r2 dots equals omega r, omega squared r. Or it may be written as r2 dots minus omega squared r equals 0. What is this? That's a differential equation which defines the unknown function r as a function of time. Unknown function, how the ring moves along the rod AB. What is the dependence of its coordinate, of the ring coordinate r, That is the distance of the ring from point A. How this distance changes in time, what is the time dependence of this coordinate. It can be found if you solve this differential equation. By the way, this differential equation looks somewhat similar to a differential equation defining the harmonic oscillations. In harmonic oscillations, you will have this type of differential equation. So this is for harmonic oscillations. This equation, we have solved it, and we know that the solution is cosine omega t or sine omega t. We discussed it. This is a differential equation describing the harmonic oscillations. And this is another differential equation which defines the motion of this ring along the rod. It differs from the equation of harmonic oscillation only by this sign of the second term here. And the solution will be different, certainly, not cosine and not sine, but something different. But do we need to know this function? Do we need to find this function? Actually, in order to solve this problem, we don't need it, because the problem asks, what is the Coriolis force? What is the Coriolis force? And the Coriolis force, by definition, is 2m omega, if we consider it in vector form, omega times velocity. Omega is the angular velocity of rotation of this rod, AB, and v is the velocity of the ring. And we need to find this Coriolis force at a certain distance, at a distance of when r equals 50 centimeters. At a certain point, we need to calculate the Coriolis force at a certain point, at a certain position of this ring on the rod. And we know at distance 50 centimeters from point A, when the ring reaches this point, when it goes through this point of 50 centimeters from the axis of rotation. At this particular point, we have to find the Coriolis force acting on the ring from the rod. And the same similar Coriolis force, the same in magnitude but opposite in direction, will act on the rod from the ring. The two forces. One force will be defined, one of these two forces equal in magnitude and oppositely directed will be defined by this formula, and another will have the same magnitude but opposite direction, that is, it will have minus sign. Which formula you are interested in depends on particular situation. Whatever sign you have to choose here, plus or minus, it depends upon what force you consider. There are two forces according to Newton's third law. Two equal forces, equal in magnitude but oppositely directed. Which force you want to find will define the sign here. Plus sign for one force and minus sign for another force. So if you, let's consider this in greater detail. Suppose there is a rotating disk and you are in the center of this rotating disk. And the disk is positioned in horizontal plane, so forces of gravity may not be taken into account. Such a disk is rotating and you are sitting here, and you let a small object slide along the disk. You let a small object slide along the disk. You just release it and the object may slide away without friction. You can draw direct lines on the surface of this disk. Will this object slide along the direct line? No. If you are sitting here on the rotating disk and you see the disk is at rest with respect to you, but everything around you is rotating because everything, the room, the wall, everything is rotating, but you are sitting on this rotating disk. which is rotating with respect to the room, and the room will be rotating with respect to you. And you release a small object, and it will slide along the surface of the disk. Will it slide along the straight line? No. You will see that the disk, that the small object slides somehow along such a trajectory. You will see it. It will not go along the straight line with respect to you or with respect to the rotating disk. It will go away from the straight line because the disk is rotating. How will you explain such motion if you are sitting here on the rotating disk? You will explain that the body is deflected from the straight line because it has some Coriolis acceleration. And in order to force this object to move along the straight line, like here, along the rod, you have to apply some force to this object. You can repeat the same experiment. You can have a rod and a small sleeve or a ring which can slide along the rod. Then, in order to force this object go along the straight line, you must apply some force in order to compensate the Coriolis acceleration. So this force will be given by this formula, and the force acting on the disk will be directed here, Coriolis force, and the force acting on the rod from the disk will be directed, will have opposite direction, will be minus F Coriolis acceleration, Coriolis force. So there are two Coriolis forces according to Newton's third law. Two forces equal in magnitude and oppositely directed and applied to different bodies. One force is applied to the ring, which slides without friction along the rod, and another force is applied to the rod from the ring in opposite direction. So whatever force you calculate, you will always have this formula, but be careful with this sign. The sign can always be obtained if velocity is here, if vector of velocity is directed here, and vector of omega, vector of angular velocity will be, in this particular case, directed perpendicular to the blackboard, to you. The vector of omega will be directed to you. Then the vector product of omega times v, you rotate this vector here, and you will find that the Coriolis force is the vector product omega times v is directed here. So this formula without minus sign, this positive formula will give you this Coriolis force, which must be applied to the ring from the rod. And if you are interested in a force applied to the rod from the ring, then you must take a minus sign. That's it. So, in order to calculate the Coriolis force, which is our purpose, our goal, according to the statement of the problem, in order to calculate this Coriolis force, we must know the mass, it's given, we must know the velocity, angular velocity of rotation, it's given in the problem, and we must know the velocity of the ring at a certain distance. We must know the velocity at certain distance r. We don't need to know the function distance as a function of time. We need to know another function, velocity, as a function of distance. But we have an equation which will give us immediately, if we solve this equation, it will give us function r of t, and we need another function, v of r. What is v? V is the first derivative of r, right? V is the first derivative of r. So the second derivative of r, which is here, is actually v dot. That is, the first term here equals v dot, the first derivative of velocity with respect to time. So the first term here is dv dt, and v is a function of time. How can we find another function, v as not a function of time, but v as a function of distance, r? How can we do it? Certainly we can solve this equation, differential equation, and find this function, and then take a derivative of it and find the velocity, but it will be the velocity as a function of time, not a velocity as a function of radius, of distance. So a small mathematical complication. We have to overcome this difficulty. How to do it? It's very simple, by the way. In order to find function v as a function of r, and we know that r is a function of t, in this particular case we can multiply this term by dr, and so that nothing changes, we can divide it by dr. We multiply and divide by the same quantity. Nothing will change. So it will give us dv dr times dr dt. Has anything changed? We had dv dt, and now we have this expression. dr can be cancelled, and what remains? dv dt. Nothing has changed because we multiplied and divided by the same quantity. Nothing has changed. But we note that dr dt is just the velocity. And this is the velocity derivative with respect to r. So what we have here is a velocity dv dr. That's a small mathematical trick. Will allow us to write down the first term in this particular way. And that will give us the possibility to solve this equation and to find the function v as a function of r, distance r, instead of r as a function of time. We will, from the same law of physics and from the same differential equation, we will find a different function, v as a function of distance. So instead of the first term, I will use this v dv dr, minus, or now it will be equal omega squared r. That's the new equation which we obtained from the first version of the same equation. But the first version was written in such a way that here was a second derivative with respect to time. And now we transformed somehow this term to be presented in another form as the first derivative with respect to distance r. This is not a derivative with respect to time. This is a derivative dv dr, and the velocity v is here. So this differential equation can be solved easily. We can multiply it by dr, and we will obtain v dv equals omega squared r dr. And after integrating, we will obtain v dv will give us v squared over 2 equal to omega squared, which is constant, r squared over 2, and plus some constant of integration which we have to define. It's easy to define it because we know the initial conditions. That is, the initial velocity was v0. It's given in the problem 1 meter per second. That is the velocity at point A. When the ring was here, it was given the initial velocity. So when distance r was 0, at this particular point, the velocity was equal to v0. It's given to us in the statement of the problem. So substitute here 0 for r and v0 for v, and we obtain that constant, which was unknown to us, now is defined. It's v0 squared divided by 2. So that v squared as a function of r, as a function of distance, I will multiply this equation by 2 immediately, will be omega squared r squared plus, and I will substitute the value found for constant plus v0 squared. I multiplied by 2 this equation. So I have found this function v as a function of r. I have found it. That's a function of r, the initial velocity, and here the constant multiplied by r squared. So the velocity as a function of r will be given by this square root of initial velocity squared plus omega squared r squared. That's the velocity, that's the necessary velocity as a function of distance. And now we can use this velocity as a function of distance to calculate the Coriolis force, which was written here as 2am omega v, and so it will be 2am omega, and instead of v, I substitute this expression square root v0 squared plus omega squared r squared equal to 2am. I will take omega squared and r squared. I will factor the square root, and that will give me omega r here, omega squared r, and square root of 1 plus v squared divided by omega squared r squared. That's the last expression may turn out to be easier to calculate than the first expression, because here in the last expression we have dimensionless figures under the square root. What it gives to us, factoring the square root by omega r, gives dimensionless, two-dimensionless terms under square root, which is easier to calculate. Just that. Though this first formula is also correct, certainly. That may be given as a final answer. But for calculation, the last formula is more convenient. And all these quantities are given in the problem. Omega is 2 radians per second, r is half meter, and initial velocity v0 is given as 1 meter per second. So everything is known, all the quantities are given and known, so that this formula may be considered to be the final answer, because everything is known, all the quantities are given in this formula. Any questions? Is everything clear? Okay. Can we go further? Okay. By the way, if anyway we want to find this function r of t, how can we do it from this? How can we find this function? How can we solve this differential equation with respect to the unknown function r of t? Is it possible? Yes. I will tell you how to do it. We can guess that this function may be something like a exponent lambda t. Let's try this function. Let's check. If this function will be a solution to this differential equation, and under what conditions this function may be a solution to this equation. So in order to check this function, we have to take the first derivative. That will be a lambda exponent lambda t. And we have to take the second derivative. We have to find r two dots, which will be a lambda squared exponent lambda t. The second derivative should be substituted for r two dots, and the first derivative should be substituted for r. And then we obtain a lambda squared exponent lambda t minus omega squared, and for r I must take a exponent lambda t equal to 0. That's our differential equation after we have substituted our formula. I don't know whether this formula will be a solution. I don't know. I'm just trying to check. If this formula will be a solution or not. So I substituted this formula into my differential equation and I obtained this result. I note immediately that exponent can be cancelled and a can be cancelled, and what remains? Lambda squared equals omega squared. If we solve this simple algebraic condition, we will obtain lambda equal plus minus omega. Either plus or minus, anything, both versions will do. Lambda may be either plus omega or minus omega. This will be satisfied in any way. So, under this condition, the formula which I have checked or tried will certainly be a solution to the differential equation, because if lambda equals plus or minus omega, then after substituting this function to my differential equation, the equation becomes an identity, like 0 equals 0. It becomes an identity. So this function will be a solution if lambda equals plus omega or minus omega. Either plus omega or minus. That means that the general solution will be a plus omega and plus another coefficient. Any coefficient a will do, because a is cancelled. So I can take another coefficient, b exponent of minus omega t. So both exponent of plus omega t and exponent of minus omega t are solutions. And therefore, as the differential equation is linear, it means that the sum of solutions will also be a solution. So this will be a solution in general case with arbitrary coefficients a and b. And here is plus omega and minus omega, and omega is just the square root of this coefficient. We cannot take omega we cannot take a different value for omega. Omega is related to this coefficient. And only under this condition that will be a solution to this equation. So we have found a solution to this equation, and the only thing we need to we have found what will be the dependence of distance of our ring which slides along the rod from the axis of rotation in this particular problem, when the ring or a sleeve was sliding along the smooth rod. So, can we obtain the same final result, which we already know, from our new function? This is not the function of velocity versus radius. This is a function of radius versus time. But can we use this function to obtain the same solution? Yes, certainly we can do it, and that's very simple. I will show you how to do it. So that I will find, along with the dependence of distance r versus time, I will find the velocity versus time. So I will differentiate it with respect to time, and the velocity will be r dot, and differentiating this function will give me a omega exponent of omega t plus b omega exponent of minus omega t. By the way, do you know why exponential function is so important in physics? What is E? E is approximately 2.718 I don't remember, 2 something, I don't remember more. Probably 5, I don't remember. Well, it's a transcendental number. Why is it so important in physics? Why this particular number is so important and it should be taken to the power of something? Do you know the secret why this number is so important? It's very important because if you consider the function f of x equal e to the power of x, then this function will possess very important property, such that df dx will equal f of x. The derivative of this function will be equal to the same function. And only this exponent has this property. No other functions have this property. That's why it's so important, because of this relationship between the function and its derivative. The derivative coincides with the function. That's it. That's why it is so important. Well, we have found here the distance of the ring from point A, from the axis of rotation, and the velocity of the same ring as a function of time. Well, what can be done? I will multiply the first equation by omega, and after that I will find the sum of two equations. The sum will be equal to v plus r omega, and that will be equal to what? Here will be omega because I multiplied by omega, and here will be omega. Sorry, I made a mistake and nobody corrected me. When I differentiated with respect to time, I have to take minus omega as a coefficient here, so there will be minus sign here. Certainly that was a slip of my chalk. So if I add these two equations, then the first terms will be the same and the second terms will be the same, but with different signs. So after adding these two equations, the first one being multiplied by omega, the second term will cancel, and the sum will be equal to what? 2a omega exponent omega t. Now I will find the difference between these two equations. I will subtract the second equation from the first one, which was preliminary multiplied by omega. In this particular case, if I subtract the second equation, the first term will vanish. The first term will cancel, and the second term will appear as double b2b omega exponent omega t. Is that correct? I multiplied. Huh? Minus. Yes, sure. Minus, yes. Now I will multiply these two equations. These two, I will multiply the second by the first one, and I will obtain v plus omega t times v minus omega t, by t, omega r, I'm in a hurry, omega r, v plus omega r multiplied by v minus omega r. Why do I want to multiply? In order to get rid of this exponent. After multiplication, these two exponents will cancel, and I will obtain 4ab omega squared. Is that correct? In order to carry out further calculations, I will notice that this is just equal to v squared minus omega squared r squared, equal to this term. And also I will need to determine coefficients a and b. I will need to determine these coefficients. How can I do it? I will use the initial conditions given in the problem. In the problem, it's known that when at the initial moment of time, when time was 0, the initial velocity was 1 meter per second, was given to v0. The initial velocity is given at the initial moment of time, when the ring was at point A. You remember this picture. At the initial moment of time, when t was 0, when t was 0, I will obtain such a condition, a omega minus b omega. If t is 0, then exponent equals to 1, 1 here and 1 here. So what remains? A omega minus b omega, and that is the initial velocity which is given in the problem v0. So also we know that at the initial moment of time, when t was 0, the distance r was also 0. The ring was at the beginning, at the axis of rotation. So this condition will give me, at the initial moment of time, when t is 0, a plus b is 0, because the distance r was 0 at the initial moment of time. And that means that b equals minus a. And by using this equation here, b equals minus a, I will obtain here a omega plus a omega. That will be 2a omega equal to v0. So 2a omega is v0, and b equals minus a. So this coefficient, this term here, may be expressed as 2a omega, which is v0, and another 2b omega, which is also minus 2a omega, which will be again v0. So we will have v0 with minus, with sign minus here. Is that correct? Something seems to be not quite so. So from here, I will not be in a hurry. From here, a equals v0 divided by 2 omega. And here, b equals minus a. Well, what's the reason behind it? I have lost a sign somewhere. I have lost a minus sign. I don't see where I have lost it. What? That's too detrimental to be in a hurry. You always lose something. So I have lost minus sign somewhere. So that this should be plus sign certainly here. That should be plus sign. It's obvious that here we must have plus sign, because when distance r is 0, according to the statement of the problem, the initial velocity must be plus v0. It cannot be minus v squared. So there must be plus here, plus v0 squared. I have lost somewhere this minus. Okay, it doesn't matter. The main thing is to find the mistake and where it was made. It's also interesting, but we don't have enough time to discuss it. So we have come to this formula where plus sign is absolutely obvious, because at the beginning of motion, when distance r was 0, the initial velocity was v0, and velocity initial squared must be positive number. It cannot be negative, so it cannot be minus sign here from general understanding. Any number squared will give you a positive number, v0 squared positive, certainly. So the final formula will be v as a function of radius. That will be v0 squared plus omega squared r squared. We have come to the same formula which we already found using different method. We already found this formula using different method. Okay, I will not lose my time, waste my time by finding where I have lost minus. But it's obvious that the final result must be with plus sign here. The final result certainly will be with plus sign, so that we have come to the same result which we have already found using different methods. So I have shown you two different methods to solve this problem. The first method was to determine the velocity as a function of distance. But that required some mathematical trick in order to obtain this function from the initial function of distance as a function of time. Initially, this equation gives you distance as a function of time here. And we understood that we don't need this function. Actually, we need not distance as a function of time, but we need a velocity as a function of distance. And we had to apply a certain mathematical trick to somehow transform this first term here, the second derivative, in such a way as to obtain this function from the differential, from a new differential equation. That was the first method of solution. And the second method of solution was demonstrated here, and it consists in direct solution of this differential equation to find the function of distance as a function versus time, distance versus time. And then, by some algebraic manipulations, we obtained from distance versus time, because if you differentiate this function, you obtain r dot, that is the velocity versus time. And if you have distance versus time and velocity versus time, can you obtain velocity versus distance? Yes, we have to exclude time. The reason behind all my algebraic transformations was very simple. We have to exclude time from these two equations, because we don't need time. We need velocity as a function of distance. So we have to exclude t. And what I have done algebraically, I multiplied by omega and then found the sum of these two equations, and then found the difference between these two equations, and then multiplied the sum by the difference, and then I obtained the equation without time. We happen to exclude time totally. We don't need it here in this particular problem. But anyway, we obtained this interesting solution. That function describes how the ring sliding on the rod will move. What will be the function of distance of the ring from the axis of rotation, the function of time? How does this distance change in time? We found this function. It's very interesting. It's exponential. It means that when time goes to infinity, this term also goes to infinity. And the velocity will be infinite. So the ring will slide along the rod. If the rod is infinitely long and rotates at a constant angular velocity, then the ring will slide along the rod and it will go to infinite velocity. Is it physically real to obtain infinite velocity? It's absolutely unreal. It's impossible. Why does this solution give us infinite velocity at infinite time in the future? Because we did not take into account elastical properties of this rod. No real rod, if it's infinite, can be rotated at some angular velocity such that all the rod rotates. If we start rotating this rod, the end of it will somehow be lagging behind, because you need to apply very strong torque in order to accelerate and organize for this rotation. And the rod will be bent somewhat behind, and the end will be lagging behind due to elasticity of any real material. And therefore, no rod will remain straight. If it's very long and you start rotating it, due to elasticity of material, it will be something like that. And if the rod is, the longer the rod, the more work you will have to apply to accelerate it and arrange for rotation at constant velocity. And if the length of the rod goes to infinity, then the work required to rotate it also tends to infinity. Is it possible to apply infinite energy? No, we don't have infinite energy on Earth. Any amount of energy is always finite. So it's impossible to rotate an infinitely large rod at constant angular velocity. It will always be bent due to elasticity of this material. It will always be deformed, which we did not take into account in this problem. That is why, as we neglected that important property, we neglected it. And that's why we obtained the solution, which appears to be inapplicable in such a situation when the rod is infinitely long and the time of sliding can be infinite. That's far away from the domain of applicability of this solution. The domain of applicability is such that this solution applies only to finite rods and finite times and finite velocities of sliding. That's it. Okay, let's finish on this point.